Welcome to Deep Science Sleep. Today we talk about gentle facts about Earth for a calm night's sleep. Opening sleep scenario. Let yourself settle into this moment. Feel the weight of your body sinking gently into whatever surface holds you. Your breathing slows naturally, each exhale releasing a little more tension than the one before. Tonight, we're going to explore something wonderfully calming, the slow, patient, enduring facts about our Earth. Not the dramatic earthquakes or volcanic eruptions, but the quiet processes that have been unfolding for billions of years with such steadiness that they make human concerns feel beautifully small and temporary. Picture yourself as a single grain of sand on an endless beach, part of something so ancient and so vast that your worries dissolve into perspective. The Earth beneath you has been turning for 4.5 billion years, and it will keep turning long after you drift into peaceful sleep. So take one more deep breath, let your eyes grow heavy, and allow these gentle facts about our planet to carry you into rest. Earth's ancient rhythms and time. The concept of deep time is perhaps one of the most soothing ideas our minds can contemplate. When we think about Earth's history, we're considering a span of approximately 4.54 billion years. That number is so large it becomes almost meaningless in its vastness, which is precisely what makes it so calming. Your entire life, every human civilization that has ever existed, all of recorded history, these are merely the thinnest imaginable slice at the very end of an incomprehensibly long story. Scientists organize this immense span using the geologic time scale, dividing Earth's history into eons, eras, periods, and epochs. The largest divisions are eons, and Earth has experienced 4 of them. The Hadean eon stretched from Earth's formation at 4.65 billion years ago until 4 billion years ago, encompassing 13% of our planet's total history. During this time, Earth was a molten, volcanic world being continuously bombarded by asteroids and comets. The planet's surface was so hot that rocks melted and flowed like water. Following the Hadean came the Archean eon, lasting from 4 billion to 2.5 billion years ago. This represents 33% of Earth's total history, a period longer than everything that would come after it. During the Archean, Earth's crust finally cooled enough to form stable continental plates. The first rocks that we can still find today date from this period, including ancient zircon crystals discovered in Western Australia that are 4.4 billion years old. These tiny crystals are the oldest terrestrial materials we've ever found, predating even the oldest rocks themselves. The Proterozoic eon followed, spanning from 2.5 billion to 541 million years ago, another vast stretch representing 42% of Earth's entire history. It was during this eon that the first complex single-celled organisms evolved, though they were still microscopic and would remain so for billions of years. The atmosphere gradually filled with oxygen, created as a waste product by photosynthesizing bacteria. This great oxygenation event fundamentally transformed Earth's chemistry and made possible all the complex life that would eventually follow. Finally, we arrive at the Phanerozoic eon, which began 541 million years ago and continues to the present day. Despite containing all the fossils we typically think about, trilobites, dinosaurs, mammals, humans, this eon represents only 12% of Earth's total history. Everything we consider ancient, from the pyramids to the earliest human ancestors to the age of dinosaurs, exists within this relatively recent chapter. What makes deep time so deeply relaxing is the perspective it offers. Geological processes unfold with such patience that they make our own timelines seem rushed by comparison. Consider continental drift, the slow movement of Earth's tectonic plates. North America and Europe are currently moving apart at a rate of about 2.5 centimeters per year, roughly the same speed at which your fingernails grow. At this pace, it would take 40 million years for the Atlantic Ocean to widen by 1,000 kilometers. Yet over hundreds of millions of years, this glacial pace has been enough to tear apart supercontinents and rebuild them in entirely new configurations. Around 750 million years ago, most of Earth's landmasses were joined together in a supercontinent called Rodinia. Over time, Rodinia broke apart, and the pieces drifted across the globe. By 600 million years ago, these fragments had reassembled into another supercontinent called Pannotia. This too broke apart, and the continents wandered separately before coming together once more around 300 million years ago to form Pangaea, the most recent supercontinent. Pangaea began fragmenting about 200 million years ago, and its pieces have been moving toward their current positions ever since. This continental dance happens so slowly that it's imperceptible within a human lifetime, yet it's relentless and unstoppable. The Himalayas rise about 5 millimeters per year as the Indian plate continues pushing into the Eurasian plate. This means that Mount Everest, Earth's tallest mountain, grows about half a meter every century. Within your lifetime, Everest will have grown by perhaps 4 or 5 centimeters, barely noticeable, yet inexorable. Erosion operates on similar timescales, wearing down mountains with the patience of eternity. Water, wind, and ice work continuously on exposed rock, breaking it down grain by grain. The Appalachian Mountains, once as tall as the Himalayas are today, have been eroding for hundreds of millions of years. They've been worn down to gentle, rounded peaks covered in forests. Given enough time, perhaps another 100 million years, they'll erode down to nearly flat plains, return to the sea as sediment. Every day, rivers carry approximately 15 billion tons of dissolved minerals and sediments from the continents to the oceans. This is erosion in action, the patient dismantling of mountains. Yet 15 billion tons, as staggering as that sounds, represents only a tiny fraction of the continental crust. At current rates, it would take approximately 100 million years to erode away the average height of the continents. And even then, tectonic forces would be building new mountains as fast as erosion could tear them down, maintaining a dynamic balance that has existed for billions of years. The formation of sedimentary rocks demonstrates this same unhurried patience. When sediments settle to the bottom of ancient seas, they accumulate in layers, one atop another, year after year, century after century, millennium after millennium. The weight of accumulating layers gradually compresses the lower sediments, squeezing out water and cementing the grains together. This lithification process takes millions of years. The limestone cliffs of Dover, formed from countless trillions of microscopic shells, represent sediments that accumulated over tens of millions of years in ancient chalk seas. Each white cliff face is a time capsule containing the remains of marine organisms that lived during the Cretaceous period, between 145 and 66 million years ago. Rock formations tell stories that span unimaginable durations. The Grand Canyon exposes nearly 2 billion years of Earth's history in its layered walls. The oldest rocks at the canyon's bottom, the Vishnu basement rocks, formed about 1.7 billion years ago. Above them, layer upon layer of sedimentary rocks accumulated over hundreds of millions of years, each representing a different ancient environment: shallow seas, river deltas, desert dunes, coastal swamps. The Colorado River, through the patient work of millions of years, carved through all these layers to create the canyon we see today. The river has been cutting downward for perhaps 5 to 6 million years, removing rock at an average rate of about 150 meters per million years. Even at its most dramatic, geological change proceeds with calm deliberation. This same patient timescale applies to the rock cycle itself. Igneous rocks form from cooling magma. Over millions of years, they're exposed at the surface through uplift and erosion. Weathering breaks them down into sediments. These sediments accumulate and lithify into sedimentary rocks. If buried deep enough, heat and pressure transform them into metamorphic rocks. Carried deeper still, they melt completely, becoming magma once again. The entire cycle, from igneous to sedimentary to metamorphic and back to igneous, typically takes hundreds of millions of years to complete. Some rocks have been through this cycle multiple times, destroyed and recreated repeatedly over the vast spans of geological time. There's something profoundly calming about contemplating processes that unfold over such immense timescales. Your anxieties, your deadlines, your regrets, all exist within the span of decades at most. Against the backdrop of deep time, they become vanishingly small, like mayflies concerned about the events of a single summer day, unaware that the forest around them has stood for thousands of years and will stand for thousands more. The earth doesn't hurry. It doesn't rush. It simply continues, patient and eternal, following physical laws that operated the same way billions of years ago and will operate the same way billions of years hence. The gentle cycles of water. Water moves through Earth's systems in what we call the hydrological cycle, a continuous journey that has been repeating for billions of years with the dependability of a heartbeat. The beauty of this cycle lies in its circularity. There's no true beginning or end, just an eternal circulation powered by the sun's energy and gravity's patient pull. The oceans contain approximately 96% of all water on Earth, about 1.338 billion cubic kilometers of salty water. This vast reservoir serves as the starting point for most water's journey through the cycle. The sun's energy constantly evaporates water from the ocean's surface, transforming liquid into vapor at a rate of about 430,000 cubic kilometers per year. This is the engine of the water cycle, solar energy lifting water molecules from the sea into the atmosphere where they can travel across continents before returning as precipitation. The water cycle proceeds with such steadiness that we take it for granted, yet its constancy is what makes life possible. Evaporation from the oceans occurs continuously, day and night, every moment of every day. The rate varies with temperature, wind speed, and humidity, but it never stops. On any given day, an average of approximately 1,000 trillion kilograms of water evaporates from Earth's oceans. This sounds dramatic, but compared to the ocean's total volume, it represents only a tiny fraction. The oceans are so vast that evaporating water at this rate for 1 million years would lower sea level by only about 30 meters. Once in the atmosphere, water vapor becomes part of the air we breathe, though we cannot see it. At any given moment, the atmosphere contains about 12,900 cubic kilometers of water in vapor form. Enough to cover the entire Earth's surface with about 2.5 centimeters of liquid water if it all precipitated at once. This atmospheric water has a relatively short residence time, averaging about 9 days before it falls as precipitation. But those 9 days allow winds to carry moisture vast distances from its source. Water that evaporates from the tropical Pacific can fall as snow in the Arctic, or rain over the Amazon, or perhaps drift back to the same ocean from which it arose. When water vapor condenses around tiny particles of dust or salt, it forms the clouds we see drifting overhead. These clouds contain water in various forms, tiny droplets too small to fall, ice crystals forming intricate geometric shapes, larger droplets that will eventually become raindrops. A single cumulus cloud might contain hundreds of tons of water, yet it floats effortlessly because the water is dispersed into billions of tiny droplets, each held aloft by air currents. The cloud drifts wherever the wind carries it, a visible manifestation of the water cycle's aerial phase. Eventually, when droplets grow large enough or ice crystals become heavy enough, they fall as precipitation. Earth receives about 505,000 cubic kilometers of precipitation each year, enough to cover the planet's surface with about 1 meter of water if distributed evenly. Of course, it isn't distributed evenly. Some regions receive several meters of rain annually, while others might go years without significant precipitation. But taken globally and averaged over time, the amount of water evaporating equals the amount precipitating, maintaining a perfect balance. When rain falls on land, it takes many different paths. Some evaporates almost immediately, returning to the atmosphere before even soaking into the ground. Some is absorbed by plants, which use a small fraction for growth and transpire the rest back into the atmosphere through tiny pores in their leaves. This transpiration is invisible but significant. A large oak tree can transpire hundreds of liters of water per day during summer. Water that soaks into the ground begins a slower journey. In the soil, it moves downward through spaces between particles, pulled by gravity but slowed by friction. Depending on the soil type, this infiltration can be fast or slow. Sandy soil drains quickly, allowing water to percolate downward at rates of several centimeters per hour. Clay-rich soil might absorb water at only a few millimeters per hour. Either way, the water is patient, moving inexorably downward through the vadose zone until it reaches the water table and becomes groundwater. Groundwater moves even more slowly than surface water. Underground, water flows through the pore spaces in rocks and sediments at rates measured in meters per year rather than meters per second. An aquifer might transport water only 100 meters over the course of a century. Some groundwater has been underground for thousands or even millions of years, slowly making its way from recharge areas in mountains toward discharge areas in valleys or along coasts. This ancient groundwater, sometimes called fossil water, was last at the surface during completely different climatic conditions, perhaps during an ice age, or during a warm period before the ice age began. The average residence time of water in different reservoirs varies dramatically. Water vapor in the atmosphere lasts only about 9 days before precipitating. Water in rivers flows toward the ocean in a matter of weeks. Water in lakes might reside there for years or even decades, depending on the lake size and the rate of inflow and outflow. Ocean water takes much longer to cycle. On average, a water molecule spends about 3,700 years in the ocean before evaporating. Groundwater can have residence times of thousands or even millions of years. Ice in glaciers and ice sheets has the longest residence time of all, sometimes remaining frozen for hundreds of thousands of years. This variation in residence times means that water molecules have vastly different experiences. Some spend eons frozen in Antarctic ice, slowly compressing under the weight of snow falling above them, before finally calving off into the ocean as part of an iceberg. Others quickly cycle through the atmosphere, falling as rain, flowing into a stream, and evaporating again within weeks. The water in your body right now contains molecules that have been rain over ancient forests, waves in prehistoric seas, snow on long-vanished glaciers, and part of countless living things throughout Earth's history. Ocean currents participate in their own grand circulation. The thermohaline circulation, sometimes called the global conveyor belt, moves water throughout the world's oceans in a journey that takes about 1,000 years to complete. Warm surface water flows from the tropics toward the poles, gradually cooling as it travels. In the North Atlantic, near Greenland and Iceland, this water becomes cold and salty enough to sink to the ocean depths. This deep water then flows southward, eventually reaching the Southern Ocean around Antarctica. From there, it spreads into the Indian and Pacific Oceans, slowly warming and gradually rising back toward the surface over hundreds of years. Eventually, it returns to the surface, warms in tropical sunlight, and begins the journey again. The Gulf Stream, part of this larger circulation, carries approximately 30 million cubic meters of water per second from the Gulf of Mexico toward northern Europe, more than 100 times the combined flow of all rivers on Earth. This enormous river within the ocean moves at speeds of 1 to 3 kilometers per hour, traveling about 40 to 120 kilometers per day. Despite moving relatively slowly, the Gulf Stream transports so much warm water that it significantly moderates the climate of Western Europe, making countries like Britain and Norway much warmer than they would otherwise be at their latitude. The constancy of these water movements is deeply soothing. Rivers have flowed to the sea for billions of years, following gravity's patient call. The Mississippi River has been carrying sediment from the continent's interior to the Gulf of Mexico for tens of millions of years, building an enormous delta from the accumulated deposits. Every day, it delivers about 500 million tons of water and 500,000 tons of sediment to the Gulf. The river doesn't hurry or slow. It simply flows, as it has always flowed, as it will continue to flow for millions of years to come, until geological forces reshape the continent in ways we cannot predict. Underground, water percolates through ancient aquifers with the patience of stone. The Ogallala Aquifer beneath the Great Plains contains groundwater that infiltrated during the last ice age, 10,000 to 30,000 years ago. This water has been slowly flowing southward underground for millennia, moving perhaps a meter or two per year through the porous rock. When pumped to the surface for irrigation, this is ancient water seeing daylight for the first time in 20,000 years, water that fell as rain when mammoths still roamed North America and glaciers covered much of the northern continent. The water cycle connects everything on Earth through its patient circulation. The rain falling outside your window might have evaporated from the Indian Ocean, traveled halfway around the world as atmospheric vapor, condensed into clouds over your region, and fallen here. In a few days or weeks, some of it will have returned to the atmosphere, perhaps to fall again on the opposite side of the planet. Water unifies Earth's systems, moving nutrients and energy, shaping landscapes, enabling life, following the same patterns it has followed for billions of years. Earth's atmospheric embrace. The atmosphere surrounds our planet like an invisible ocean, held in place by gravity, extending from the surface up through gradually thinning layers until it finally fades into the vacuum of space. This blanket of gases is so essential to life that we rarely think about it, yet it performs countless functions every moment, protecting and nurturing the biosphere with quiet constancy. Earth's atmosphere is composed primarily of nitrogen, making up 78% of dry air by volume. Nitrogen is largely inert, meaning it doesn't readily react with other substances under normal conditions. This inertness is actually beneficial. It dilutes oxygen and prevents the rapid, uncontrolled burning that would occur in a pure oxygen atmosphere. Nitrogen also plays a crucial role in biology, as all living things need nitrogen to build proteins and nucleic acids, though most organisms cannot use atmospheric nitrogen directly and must obtain it through other sources. Oxygen comprises about 21% of the atmosphere. This oxygen is not a remnant of Earth's formation. The early atmosphere contained almost no free oxygen. Instead, essentially all atmospheric oxygen has been produced by photosynthetic organisms over billions of years, making it one of life's greatest gifts to the planet. The current oxygen level represents a careful balance, high enough to support animal respiration and combustion, but not so high that fires would burn out of control. If oxygen levels were just a few percentage points higher, even wet vegetation could burn easily, and lightning strikes would ignite devastating wildfires that would be nearly impossible to extinguish. Argon makes up about 0.93% of the atmosphere. It's a noble gas, meaning it doesn't react with anything at all. Argon atoms drift through the air completely inert, neither helping nor harming anything, simply present as they have been for billions of years. Carbon dioxide, despite its significance for climate and photosynthesis, comprises only about 0.04% of the atmosphere, 400 parts per million. Though small in concentration, carbon dioxide plays an outsized role in regulating Earth's temperature and providing the carbon that all organic life requires. The remainder of the atmosphere consists of trace gases in even smaller quantities. Neon, helium, methane, krypton, hydrogen, and others, each present in amounts measured in parts per million or even parts per billion. Despite their tiny concentrations, some of these trace gases have important effects. Ozone in the stratosphere, though only present in amounts of a few parts per million, absorbs most of the sun's ultraviolet radiation, protecting life at the surface from this harmful energy. Water vapor, though not counted in the composition of dry air, is another critical component, varying from nearly 0% in cold, dry regions to about 4% in hot, humid tropical areas. Water vapor is a greenhouse gas. It traps infrared radiation trying to escape to space, helping keep Earth's surface warm enough for liquid water to exist. The greenhouse effect created by water vapor, carbon dioxide, and other gases makes Earth about 33 degrees Celsius warmer than it would be otherwise. Without this natural greenhouse effect, average global temperatures would be well below freezing, the oceans would be ice, and Earth would be inhospitable to complex life. The atmosphere is structured in layers defined by how temperature changes with altitude. The lowest layer, the troposphere, extends from the surface up to about 12 kilometers at mid-latitudes. Nearly all weather occurs in the troposphere, and it contains about 75% of the atmosphere's total mass. In the troposphere, temperature generally decreases with altitude at a rate of about 6.5 degrees Celsius per kilometer. This happens because the sun primarily heats Earth's surface, and the surface then warms the air above it. Higher air is farther from this heat source and therefore colder. Above the troposphere lies the stratosphere, extending from roughly 12 to 50 kilometers above the surface. In the stratosphere, temperature actually increases with altitude, the opposite of what happens in the troposphere. This temperature inversion occurs because the stratosphere contains the ozone layer, and ozone absorbs ultraviolet radiation from the sun. This absorption converts UV energy into heat, warming the stratospheric air. The temperature inversion makes the stratosphere stable. Warm air sits above cold air, with no tendency to mix, which is why the stratosphere has almost no weather and why commercial aircraft fly in the lower stratosphere to avoid the turbulence common in the troposphere below. The mesosphere extends from about 50 to 85 kilometers above Earth's surface. Here, temperature again decreases with altitude, reaching the coldest temperatures found anywhere in Earth's atmosphere, as low as -90 degrees Celsius at the mesosphere's upper boundary. The mesosphere is too high for weather balloons and too low for satellites, making it one of the least studied regions of the atmosphere. Yet it plays an important role. Meteors entering Earth's atmosphere burn up in the mesosphere due to friction with air molecules, creating the shooting stars we see on clear nights. The mesosphere protects us by vaporizing countless small meteoroids that would otherwise reach the surface. Above the mesosphere lies the thermosphere, extending from about 85 kilometers up to 600 kilometers or more. Despite its name suggesting warmth, the thermosphere's high temperatures, which can exceed 1,500 degrees Celsius, would not feel hot because the air is so thin. With few molecules present, there's very little matter to transfer heat. The thermosphere is where auroras occur, when charged particles from the sun interact with atmospheric gases, creating the shimmering curtains of light we call the aurora borealis and aurora australis. This layer also contains the ionosphere, a region where solar radiation ionizes atoms, creating charged particles that reflect certain radio waves, making long-distance radio communication possible. Finally, the exosphere forms the outermost layer of Earth's atmosphere, extending from about 600 kilometers up to 10,000 kilometers. Here, the atmosphere is so thin that molecules can travel kilometers without colliding with other molecules. Some molecules in the exosphere achieve escape velocity and drift off into space, slowly but continuously depleting Earth's atmosphere. However, this loss is extremely slow. It would take billions of years to significantly deplete the atmosphere through this mechanism. The exosphere gradually blends into the vacuum of interplanetary space, with no sharp boundary defining where Earth's atmosphere ends and space begins. Atmospheric pressure decreases exponentially with altitude. At sea level, the atmosphere exerts a pressure of about 101,325 pascals, or 1.01 bar. This pressure represents the weight of all the air above, a column of atmosphere extending upward for hundreds of kilometers. We don't feel crushed by this pressure because our bodies have evolved at this pressure and our internal fluids exert an equal outward pressure. At the top of Mount Everest, 8,849 meters above sea level, atmospheric pressure is only about 1/3 of sea level pressure. The air is so thin that the human body cannot extract enough oxygen from it, requiring climbers to use supplemental oxygen. At the altitude where commercial aircraft fly, about 10 to 12 kilometers, pressure is only about 1/4 of sea level pressure, necessitating pressurized cabins. The atmosphere's protective functions are numerous and vital. It shields us from most meteoroids, burning them up before they can reach the surface. It blocks harmful ultraviolet radiation that would otherwise damage DNA and make terrestrial life impossible. It moderates temperature extremes between day and night. Without an atmosphere, Earth's surface would swing from extreme heat in sunlight to extreme cold in shadow, much like the Moon experiences temperature variations from plus 120 degrees Celsius in sunlight to minus 170 degrees Celsius in shade. The atmosphere also distributes heat around the planet through wind patterns driven by unequal solar heating. The equator receives more solar energy than the poles, creating temperature differences that drive atmospheric circulation. Warm air rises at the equator, moves toward the poles at high altitude, sinks in the subtropical regions, and returns toward the equator at the surface. This creates cells of circulation that transport heat from warm regions to cooler ones, moderating the temperature extremes that would otherwise exist. Without this atmospheric heat transport, the tropics would be unbearably hot and the poles even colder than they are. The constancy of the atmosphere's composition and behavior is deeply reassuring. For hundreds of millions of years, oxygen levels have remained relatively stable, maintained by a balance between oxygen production through photosynthesis and oxygen consumption through respiration and decay. The atmosphere's structure, troposphere, stratosphere, mesosphere, thermosphere, has persisted for billions of years, governed by unchanging physical laws. The protective shield the atmosphere provides against radiation and space debris has been in place since Earth developed its current atmosphere, making complex life possible. Every breath you take draws in this ancient mixture of gases. The nitrogen molecules entering your lungs might have been part of the atmosphere for billions of years, cycling through countless organisms but always returning unchanged. The oxygen you breathe was likely produced by photosynthetic organisms somewhere on Earth within the past few thousand years, perhaps by a tree in a temperate forest, or by phytoplankton in the open ocean, or by prairie grasses swaying in the wind. With each exhalation, you return carbon dioxide to the atmosphere, where it will eventually be absorbed by a plant somewhere and transformed back into oxygen and organic matter, continuing cycles that have operated for eons. The silent language of rocks and minerals. Minerals form the building blocks of rocks, and rocks form the solid foundation of our planet's crust. These substances, seemingly inert and lifeless, are actually the products of processes playing out over vast timescales, processes that continue today as they have for billions of years, following chemical and physical laws with perfect consistency. Minerals are naturally occurring solid substances with definite chemical compositions and ordered atomic structures. This orderliness at the atomic level gives minerals their characteristic properties, their hardness, their color, how they break, how they interact with light. A mineral's internal structure is like a three-dimensional lattice, with atoms arranged in repeating geometric patterns that extend throughout the entire crystal. This crystalline structure forms as atoms or molecules in a liquid or gas slow down enough to bond with each other in organized ways. The most common way minerals form is through crystallization from molten rock, or magma. Deep within Earth's interior, temperatures are high enough to melt rock. This magma contains dissolved ions of many elements: silicon, oxygen, iron, magnesium, calcium, sodium, potassium, and others. As the magma cools, these ions begin bonding together in organized patterns, forming mineral crystals. The rate of cooling determines the size of the crystals that form. Slow cooling deep underground allows large crystals to grow, sometimes reaching spectacular sizes, individual crystals several meters long in some pegmatites. Rapid cooling at the surface produces tiny crystals or even prevents crystallization altogether, forming volcanic glass like obsidian. The sequence in which minerals crystallize from cooling magma follows predictable patterns discovered by geologist Norman Bowen in the early 20th century. Minerals rich in iron and magnesium crystallize first at high temperatures. As cooling continues and these early minerals are removed from the melt, the remaining liquid becomes enriched in silica. At progressively lower temperatures, minerals with more complex crystal structures crystallize, eventually ending with quartz and the feldspars at the lowest crystallization temperatures. This orderly sequence, known as Bowen's reaction series, explains the mineral compositions of different types of igneous rocks and demonstrates how geological processes follow orderly, predictable patterns. Minerals also form through precipitation from aqueous solutions. Water can dissolve many minerals, especially at high temperatures and pressures. When conditions change, through cooling, evaporation, or chemical reactions, dissolved ions may come out of solution and crystallize. This is how minerals form in hydrothermal veins, in cave formations, and in evaporite deposits like salt flats. Halite, or common table salt, crystallizes when seawater or brine in salt lakes evaporates, concentrating dissolved sodium and chlorine ions until they bond together and precipitate as cubic crystals. The formation of cave minerals like stalactites and stalagmites demonstrates crystallization's patient work. Groundwater seeping through limestone dissolves small amounts of calcium carbonate. When this water reaches an air-filled cave and carbon dioxide escapes from the drip, the calcium carbonate precipitates out, adding a microscopically thin layer to the growing formation. A typical stalactite might grow 1 cubic centimeter over 100 years, meaning that large stalactites several meters long have been growing continuously for hundreds of thousands of years, one molecule at a time, in darkness and silence, driven by nothing more than chemistry and gravity. Crystal formation requires time for atoms to find their correct positions in the growing structure. If time is limited, crystals remain small or don't form at all. This is why rapid cooling of lava produces volcanic glass. The magma solidifies before atoms can organize into crystalline structures. With adequate time, even glass will slowly crystallize. Obsidian, volcanic glass formed from rapid cooling, will gradually devitrify over millions of years, developing tiny crystals within the formerly amorphous material. Given enough time, essentially all glass eventually becomes at least partially crystalline. Some minerals form through metamorphism, when existing rocks are subjected to high temperature and pressure deep within Earth's crust. The heat and pressure cause atoms in the original minerals to rearrange, forming new minerals more stable under the new conditions. Limestone, a sedimentary rock composed of calcite, transforms into marble when metamorphosed. Shale transforms into slate, then schist, then gneiss as metamorphic intensity increases. New minerals appear at each step: muscovite, garnet, staurolite, kyanite, each stable only within certain temperature and pressure ranges. By identifying the metamorphic minerals in a rock, geologists can determine the conditions under which it formed, even if those conditions existed hundreds of millions of years ago. The variety of minerals on Earth is remarkable. Over 5,400 different mineral species have been identified, each with its unique composition and structure. Yet despite this diversity, only about 100 minerals are common, and just 8 minerals make up the vast majority of Earth's crust. Quartz, orthoclase feldspar, plagioclase feldspar, muscovite, biotite, amphibole, pyroxene, and olivine. These 8 minerals, all silicates containing silicon and oxygen, constitute more than 90% of the continental crust. Quartz is particularly stable and abundant. Its simple chemical formula, silicon dioxide, and strong crystal structure make it resistant to both chemical weathering and physical breakdown. When granite weathers, many of its minerals decompose into clay, but quartz grains survive intact, accumulating as sand. Over time, this sand might be lithified into sandstone. If the sandstone is metamorphosed, it becomes quartzite, where quartz grains fuse together. Through all these transformations, the quartz persists, demonstrating a durability that spans hundreds of millions of years. Feldspars, though less stable than quartz, are even more abundant, making up about 60% of Earth's crust. When feldspar weathers, it breaks down into clay minerals, which form the basis of soils. This transformation is one of the most important weathering processes on Earth, slowly converting solid rock into the medium that supports terrestrial plant life. The process is extremely slow. A crystal of feldspar might take millions of years to weather completely in a temperate climate. Yet given sufficient time, even the hardest rock is reduced to clay and sand. Some minerals form through biological processes. Calcium carbonate shells created by marine organisms accumulate on the seafloor, eventually lithifying into limestone. Bone and tooth enamel contain the mineral apatite, a calcium phosphate. These biologically formed minerals are still considered minerals because they can also form inorganically, and they have the same chemical composition and crystal structure regardless of their origin. The distinction between living and non-living becomes blurred at this fundamental level. Life builds itself from the same chemical elements and follows the same physical laws as the non-living world. Minerals can also be destroyed or transformed. When rocks are heated sufficiently, their constituent minerals melt, losing their crystal structure and becoming part of a magma. The minerals cease to exist as distinct entities, though their chemical components persist in the melt, ready to recombine into new minerals when the magma cools. This destruction and reformation is part of the rock cycle, a grand recycling process operating over hundreds of millions of years. The oldest terrestrial minerals yet discovered are detrital zircon crystals from the Jack Hills of Western Australia, dated at 4.4 billion years old. These tiny crystals, smaller than a grain of sand, survived when the rocks that once contained them eroded away. They were incorporated into younger sediments, which lithified into conglomerate. The zircons persisted through all these transformations, carrying within their crystal structure a record of Earth's earliest history. The chemistry of these ancient zircons suggests that liquid water and possibly even continents existed on Earth much earlier than previously thought, within a few 100 million years of our planet's formation. The stability of minerals over geological time is remarkable. A crystal formed 1 billion years ago, if protected from weathering and metamorphism, would be indistinguishable from one formed yesterday. The atomic bonds are just as strong, the crystal structure just as perfect. Minerals don't age or deteriorate spontaneously, they're stable indefinitely under the right conditions. A diamond formed 2 billion years ago in Earth's mantle, then brought to the surface by volcanic activity, is as perfect today as when it first crystallized. The carbon atoms in that diamond have been bonded together, unchanged, for half of Earth's history. There's something deeply calming about the patience of mineral formation and the stability of crystals once formed. These processes don't hurry, yet they're relentless. A limestone cave grows its formations one drop at a time, one molecule at a time, year after year, century after century, millennium after millennium, undisturbed and unhurried. A crystal growing in a pegmatite cavity adds atoms to its faces slowly but steadily, following the precise geometry dictated by its internal structure, until conditions change or space runs out. These processes operated in the same way billions of years ago and will continue operating in the same way billions of years from now, indifferent to the passage of civilizations, unaffected by the concerns of any living thing. Life's patient evolution on Earth. The story of life on Earth is one of almost incomprehensible patience, stretching back approximately 3.8 billion years to the first simple cells. Evolution doesn't happen quickly. It accumulates small changes over millions of generations, guided by natural selection, genetic drift, and other mechanisms that shape populations gradually, almost imperceptibly, over vast stretches of time. The earliest evidence of life comes from microscopic fossils and chemical signatures in rocks from Western Australia and Greenland dating to about 3.7 to 3.8 billion years ago. These earliest organisms were single-celled, lacking nuclei, likely similar to modern bacteria. They lived in oceans, obtaining energy either from chemicals in hydrothermal vents or perhaps from primitive forms of photosynthesis. These simple cells would remain the only form of life on Earth for approximately 2 billion years, more than half of life's total history. This extended period with only single-celled life demonstrates evolution's patience. For 2 billion years, cells gradually became more efficient at metabolism, developed different ways of obtaining energy, evolved resistance to various environmental stresses, and diversified into different ecological niches, yet remained fundamentally simple in structure. There was no hurry, no rush toward complexity. Single-celled organisms were successful, and success in evolutionary terms simply means surviving and reproducing. Complexity offers no inherent advantage unless environmental conditions favor it. Around 2 billion years ago, something remarkable happened. One cell engulfed another, but instead of digesting it, the two formed a partnership. The engulfed cell, likely a bacterium capable of aerobic respiration, became a permanent resident, eventually evolving into mitochondria, the powerhouses of modern eukaryotic cells. This endosymbiotic event happened only once or perhaps a few times in Earth's history, but it enabled the evolution of all complex life, animals, plants, fungi, and protists all descended from this ancient partnership. Similarly, chloroplasts in plants originated from cyanobacteria that entered into symbiosis with early eukaryotic cells, bringing the capacity for photosynthesis with them. Yet even after eukaryotic cells evolved, multicellular life didn't emerge immediately. Single-celled eukaryotes dominated for over 1 billion years more. The first multicellular organisms appeared perhaps 1.5 to 2 billion years ago, but these early forms were simple, with limited differentiation between cell types. It took until about 600 million years ago, during what's called the Ediacaran period, for complex multicellular organisms to diversify significantly. The Ediacaran fauna were strange creatures, unlike anything alive today. Some resembled quilted fronds, others looked like discs or spindles, and their relationships to modern organisms remain uncertain. They lived on or in the seafloor, feeding on bacteria or dissolved nutrients, moving little if at all. These organisms had no shells, no teeth, no obvious means of defense. The seafloor of the Ediacaran was a peaceful place. Predation as we understand it didn't yet exist. Organisms didn't need to run or hide or fight, because nothing was chasing them. This changed during the Cambrian explosion, beginning around 541 million years ago. Over a period of perhaps 20 million years, rapid by geological standards but still encompassing more generations than we can meaningfully comprehend, most major animal body plans evolved. Trilobites, brachiopods, primitive mollusks, early arthropods, and various other groups appeared in the fossil record. Many developed hard shells or exoskeletons, leaving fossils far more readily than their soft-bodied Ediacaran predecessors. The evolution of predation likely drove much of this diversification. Once some animals began eating others, evolutionary pressure favored defensive structures like shells, as well as sensory organs to detect predators and appendages for movement or escape. Yet even during this explosion, evolution proceeded one generation at a time, one small change at a time. A mutation might alter a protein structure slightly, making an organism marginally more likely to survive and reproduce. Its offspring would inherit this change, and if they also survived better than average, the mutation would spread through the population over many generations. Repeat this process millions of times, with thousands of different mutations, over millions of years, and simple organisms gradually transform into complex ones. The fossil record shows both the gradual nature of evolution and its occasional rapid shifts. Horseshoe crabs have remained essentially unchanged for 450 million years. They found a successful body plan and ecological niche, and natural selection maintained that form because it worked. Other lineages changed more dramatically. Fish evolved from jawless ancestors to jawed forms, developed lungs and limbs to become the first tetrapods, adapted to life on land, diversified into amphibians and reptiles, eventually giving rise to mammals and birds through distinct lineages. Each transition took millions of years and involved countless intermediate forms, most of which we'll never find as fossils. The invasion of land by plants and animals represents another slow transformation. Plants likely began colonizing land around 470 million years ago, initially as simple moss-like organisms hugging moist surfaces. Over millions of years, they evolved roots to anchor themselves and extract nutrients, vascular tissues to transport water and nutrients, and increasingly sophisticated structures for reproduction in dry environments. By 360 million years ago, vast forests of tree-sized ferns and early seed plants covered the land, creating entirely new habitats for animal life. Animals followed plants onto land, initially as arthropods, ancestors of insects and spiders, that could survive in the moist forest floor litter. Later, certain fish adapted to life in shallow, oxygen-poor waters by developing lungs to breathe air. Some of their descendants eventually spent more time on land than in water, and over millions of years, their fins evolved into limbs capable of supporting their weight. These early tetrapods gave rise to amphibians, which in turn gave rise to reptiles, animals that could complete their entire life cycle on land, independent of water for reproduction. The age of dinosaurs lasted approximately 165 million years, from the Triassic period beginning 252 million years ago through the Cretaceous period ending 66 million years ago. During this enormous span, dinosaurs evolved into forms ranging from chicken-sized to the largest land animals that have ever existed. Sauropods like Argentinosaurus may have weighed up to 100 metric tons and measured more than 30 meters in length. These giants moved slowly but constantly, consuming hundreds of kilograms of plant matter daily to fuel their enormous bodies. Their lives were measured in decades or perhaps even a century or more, a long time by animal standards, but a mere instant in geological time. The extinction of non-avian dinosaurs 66 million years ago, likely caused by an asteroid impact combined with massive volcanic eruptions, demonstrates that evolution responds to environmental change. The impact winter that followed the asteroid strike, with its global darkness and temperature drop, favored small organisms that could shelter and survive on limited resources. Mammals, which had existed alongside dinosaurs for over 150 million years but had remained small and mostly nocturnal, suddenly found ecological opportunities opening. Over the following millions of years, mammals diversified to fill the niches previously occupied by dinosaurs, evolving into forms ranging from tiny shrews to massive whales. The evolution of whales exemplifies the gradual nature of major transitions. About 50 million years ago, some mammals living along coastlines began spending more time in water, perhaps hunting fish or avoiding terrestrial predators. Over millions of years, their descendants became increasingly adapted to aquatic life. Front limbs gradually transformed into flippers, hind limbs reduced and eventually disappeared, the tail developed flukes, the nostrils migrated to the top of the head to become a blowhole, and body shape became streamlined. Fossil intermediates preserve each stage of this transformation, showing creatures that were neither fully terrestrial nor fully aquatic, but somewhere in between, each form successful in its own time and environment. Human evolution shows similar gradualism. The human lineage split from other apes approximately 6 to 7 million years ago, but recognizably human features evolved slowly. Early hominins walked upright but had small brains, large teeth, and ape-like proportions. Over millions of years, brain size gradually increased, teeth became smaller, faces became flatter, and body proportions shifted toward modern human form. Anatomically modern humans, Homo sapiens, appeared around 300,000 years ago, but humans with fully modern behavior, complex language, symbolic thinking, advanced tool use, may have emerged only within the past 100,000 years or less. Even after modern humans evolved, most of human existence was spent as nomadic hunter-gatherers. Agriculture developed only about 12,000 years ago, and civilization in the form of cities and writing only about 5,000 years ago. All of recorded history, everything from ancient Egypt and Sumer through classical antiquity, the Middle Ages, the Renaissance, the Industrial Revolution, to the present day, occupies only the most recent 0.1% of the time since anatomically modern humans first appeared, and only about 0.001% of the time since complex life evolved. Extinction is as much a part of evolution as diversification. More than 99% of all species that have ever existed are now extinct. Most extinctions happen gradually, as environments change and species fail to adapt quickly enough. But the fossil record also reveals 5 mass extinction events, times when more than 75% of species disappeared in geologically brief periods. The most severe, the Permian-Triassic extinction about 252 million years ago, killed approximately 95% of marine species and 70% of terrestrial vertebrate species. Recovery from this extinction took millions of years, but life persisted, diversified again, and filled the ecological void left by the vanished species. These extinction events demonstrate life's resilience. No matter how severe the catastrophe, some organisms survive, and from these survivors, diversity gradually rebuilds. Life has persisted on Earth through asteroid impacts, supervolcanic eruptions, ice ages that covered most continents in glaciers, periods of extreme warmth, episodes of low oxygen in the oceans, and dramatic shifts in atmospheric composition. Through all these changes, life adapted, survived, and diversified, demonstrating a persistence that spans billions of years. Microorganisms demonstrate evolution's continuing work. Bacteria can evolve resistance to antibiotics within years or even months when exposed to selection pressure. This happens because bacteria reproduce rapidly, have large populations, and occasionally undergo mutations that confer antibiotic resistance. These resistant individuals survive when antibiotics are present, reproduce, and pass the resistance to their offspring. Within a surprisingly short time by evolutionary standards, the entire population may become resistant. This same process, operating over millions of years instead of years, drives all evolutionary change. Evolution has no goal or direction, it simply reflects which individuals survive and reproduce in their particular environment. Organisms don't evolve toward perfection, only toward adequacy for their current circumstances. A cave-dwelling fish that has lost its eyes through evolution isn't less evolved than its sighted ancestors. It's differently evolved, adapted to an environment where eyes provide no benefit and maintaining them would waste energy. Evolution tinkers with whatever variation exists, favoring changes that improve survival and reproduction in the current environment, indifferent to past forms or future possibilities. The patient accumulation of small changes over vast time produces outcomes that would seem impossible if we only considered short timescales. A modern human and a chimpanzee differ by only about 1 to 2% in their DNA sequences, yet this small difference accumulated over 6 to 7 million years produces profoundly different organisms. The differences emerged gradually, slightly different patterns of brain growth, slightly different proportions of limb bones, slightly different patterns of gene expression, each change small, but collectively transformative over millions of generations. There's something deeply peaceful about evolution's indifference to urgency. Natural selection doesn't hurry. Populations change as the individuals best suited to their environment leave more offspring, generation after generation, for as long as necessary. There's no schedule, no deadline, no pressure to achieve complexity or intelligence or any particular form. Life simply continues, adapting to whatever conditions exist, persisting through changes that would seem catastrophic from an individual perspective, yet are merely part of the pattern when viewed across deep time. Earth's magnetic and gravitational constants. Earth generates a magnetic field that extends tens of thousands of kilometers into space, creating an invisible shield called the magnetosphere. This field has existed for at least 3.45 billion years, protecting Earth's atmosphere from the solar wind, a constant stream of charged particles flowing outward from the Sun. Without this magnetic shield, Earth might have lost much of its atmosphere over geological time, as Mars apparently did after its magnetic field weakened and ultimately disappeared. The magnetic field originates deep within Earth's core, where liquid iron moves in complex patterns driven by heat escaping from the planet's interior and by Earth's rotation. This movement of electrically conductive fluid generates electric currents, which in turn create magnetic fields. The process, called the geodynamo, operates continuously, converting thermal and kinetic energy into magnetic energy. As long as Earth's interior remains hot enough to keep the outer core liquid and convection continues, the magnetic field will persist. The magnetic field strength at Earth's surface averages about 25 to 65 microteslas, depending on location. This is roughly 100 times weaker than a typical refrigerator magnet, yet strong enough to orient compass needles and guide migrating birds and other animals that use magnetic cues for navigation. The field strength has varied over geological time, sometimes much stronger than today, sometimes weaker. Currently, the field appears to be weakening at a rate of about 5% per century, though this may be part of normal fluctuations rather than indicating an impending reversal. Earth's magnetic field reverses polarity at irregular intervals, with the north and south magnetic poles swapping positions. The last reversal occurred about 770,000 years ago. Before that, reversals happened more frequently, about 4 times per million years on average over the past 20 million years, though the rate has varied considerably over Earth's history. Some reversals occurred within a few thousand years, rapid by geological standards but still spanning many human lifetimes. During a reversal, the magnetic field weakens and becomes chaotic, with multiple magnetic poles appearing at various latitudes before eventually reorganizing into a reversed configuration. The weakened field during reversal transitions may allow more cosmic radiation to reach Earth's surface, though the atmosphere still provides substantial protection. Despite numerous reversals throughout Earth's history, there's no evidence that reversals caused mass extinctions or catastrophic environmental changes. Life continued through each reversal, apparently unbothered by the magnetic field's temporary weakness. The magnetosphere deflects and captures charged particles from the solar wind, preventing them from directly striking Earth's atmosphere. Some particles become trapped in regions called the Van Allen radiation belts, 2 donut-shaped zones of intense radiation encircling Earth at altitudes of approximately 1,000 to 60,000 kilometers. These belts contain high-energy electrons and protons trapped by Earth's magnetic field, bouncing back and forth between the field's north and south poles. When particularly intense solar storms eject massive amounts of charged particles toward Earth, these particles can overwhelm the magnetosphere's defenses, penetrating to lower altitudes where they collide with atmospheric gases. These collisions excite the atoms and molecules in the upper atmosphere, causing them to emit light in the spectacular displays we call auroras. The aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere occur in oval zones around the magnetic poles, visible on clear nights when solar activity enhances the normally steady but faint auroral emissions. Gravity provides another constant force shaping Earth and everything on it. Earth's gravitational field results from its mass, approximately 5.97 times 10 to the 24th power kilograms of rock, metal, water, and air. This enormous mass warps spacetime around it, creating what we experience as gravitational attraction. At Earth's surface, this produces an acceleration of 9.8 meters per second squared, meaning that a dropped object accelerates downward at this rate, gaining 9.8 meters per second of velocity for each second it falls, neglecting air resistance. Gravity's strength varies slightly across Earth's surface because Earth isn't perfectly spherical and its mass isn't uniformly distributed. The planet bulges slightly at the equator due to its rotation, making the equatorial radius about 21 kilometers larger than the polar radius. Because gravity weakens with distance from Earth's center, locations at the equator, being farther from the center, experience slightly weaker gravity than locations at the poles. Additionally, variations in crustal thickness and density cause small local differences in gravitational strength. These variations are tiny, rarely more than 0.5% from the average, but sensitive instruments can detect them, and scientists use these measurements to map subsurface geological structures. The Moon's gravity creates tides in Earth's oceans, and to a lesser extent in the solid Earth itself. As the Moon orbits Earth, its gravitational pull creates a bulge in the ocean on the side facing the Moon and another bulge on the opposite side. Earth rotates beneath these bulges, causing most coastlines to experience 2 high tides and 2 low tides each day. The Sun also contributes to tides, though more distant than the Moon. The Sun's enormous mass gives it about 46% of the Moon's tide-raising force. When the Moon and Sun align during new and full moons, their tidal effects combine to produce especially high spring tides. When they're at right angles during quarter moons, their effects partially cancel, producing smaller neap tides. Tidal friction gradually slows Earth's rotation, lengthening the day by about 1.7 milliseconds per century. This happens because the tidal bulges in the ocean don't align exactly with the Earth-Moon line. Earth's rotation carries the bulges slightly ahead. The Moon's gravity pulls back on these bulges, creating a torque that slows Earth's rotation. By Newton's third law, Earth simultaneously exerts an equal and opposite force on the Moon, accelerating it in its orbit and causing it to spiral very slowly outward, receding from Earth at about 3.8 centimeters per year. 400 million years ago during the Devonian period, when the Moon was closer to Earth, days were approximately 21.5 hours long, and a year contained about 400 days. We know this from growth patterns in fossil corals, which add daily and yearly growth bands that record both the length of the day and the number of days per year. These ancient corals are natural clocks, preserving evidence of Earth's rotation rate in their skeletons. Continuing the trend forward, billions of years from now, Earth's rotation will slow until one face permanently points toward the Moon, just as the Moon currently keeps one face toward Earth. At that point, tidal forces will have locked Earth and Moon into synchronous rotation. Earth's rotation serves multiple purposes beyond creating day and night. The Coriolis effect, caused by Earth's rotation, deflects moving fluids to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection influences ocean currents and atmospheric circulation, creating the characteristic spiral patterns of hurricanes and the west-to-east flow of the jet stream. Without Earth's rotation, global wind patterns would be completely different. Air would flow directly from high pressure to low pressure regions without the curved paths we observe. The stability of Earth's axial tilt, maintained by the Moon's gravitational influence, has been crucial for long-term climate stability. Earth's axis currently tilts 23.4 degrees relative to its orbital plane, creating the seasons by varying the directional concentration of sunlight each hemisphere receives throughout the year. This tilt oscillates between 22.1 and 24.5 degrees over a cycle of about 41,000 years, one of several orbital variations that contribute to ice age cycles. Without the Moon to stabilize it, Earth's axial tilt would vary chaotically over millions of years, potentially ranging from 0 to 85 degrees or more, causing dramatic climate instability that might have prevented complex life from evolving. Mars, lacking a large stabilizing moon, has experienced such chaotic variations in its obliquity, swinging from near 0 to more than 60 degrees, producing enormous climate swings. Earth's climate has varied considerably over geological time, but these variations have been relatively modest compared to what might have occurred without the Moon's stabilizing influence. Gravity shapes not just Earth's form but also the distribution of matter within it. Denser materials sank toward the planet's center early in Earth's history, while lighter materials rose to the surface, creating a stratified structure with a dense iron-nickel core surrounded by a less dense silicate mantle and an even less dense crust. This differentiation occurred when Earth was young and mostly or entirely molten, allowing gravity to sort materials by density over millions of years. The structure persists because while the mantle flows very slowly over geological time, the density differences are great enough that remixing cannot occur. The dense core remains at the center, where gravity confined it billions of years ago. These fundamental forces, gravity and magnetism, operate continuously without variation, following physical laws that have remained constant throughout Earth's history. The magnetic field fluctuates in strength and periodically reverses, but the dynamo process continues. Gravity's strength at Earth's surface has remained essentially constant for billions of years, varying only slightly as the Moon slowly recedes and Earth's rotation gradually slows. These are processes measured in millions and billions of years, changes so slow that from a human perspective they might as well be eternal. The underground world. Beneath our feet extends a largely unknown realm of caves, aquifers, underground rivers, and vast networks of pore spaces filled with ancient water. This subterranean world, invisible and largely inaccessible, follows its own slow rhythms, shaped by water's patient work over millions of years. Caves form primarily through dissolution, water slowly dissolving soluble rock. Limestone caves, the most common type, develop when slightly acidic groundwater flows through fractures in limestone formations. Carbon dioxide from the atmosphere and soil dissolves in rainwater, forming weak carbonic acid. This acid reacts with calcium carbonate in limestone, dissolving it and carrying the dissolved mineral away in solution. Over thousands to millions of years, small fractures gradually enlarge into passages, which can eventually grow into vast chambers. The rate of cave formation depends on factors including the solubility of the rock, the acidity of the water, the flow rate of groundwater, and the hydraulic gradient. In favorable conditions, a passage might enlarge by about 1 mm per century. This means that a cave passage 10 meters wide might have required 10,000 centuries, 1 million years, to form. Some caves are much older. Mammoth Cave in Kentucky, the world's longest known cave system with over 650 kilometers of surveyed passages, has been forming for approximately 10 million years, with different levels of passages representing different positions of the water table over that time. Inside caves, groundwater creates formations called speleothems through precipitation of dissolved minerals. When water seeping through rock reaches an air-filled cave passage, carbon dioxide escapes from the drip, reducing the water's capacity to hold dissolved calcium carbonate. The mineral precipitates out, adding to growing formations. Stalactites hang from cave ceilings, growing downward as each drip deposits a microscopically thin layer of calcite. Stalagmites build upward from the floor where drips land. Columns form when stalactites and stalagmites meet. Flowstone deposits create flowing shapes where water runs down cave walls or across floors. The rate of speleothem growth varies with water flow, mineral concentration, and carbon dioxide levels, but it's invariably slow. A typical stalactite might grow 1 cubic centimeter per century, meaning that a stalactite 1 meter long could be hundreds of thousands of years old. Some speleothems are much older. Uranium-thorium dating of speleothems in some caves has revealed ages exceeding 1 million years. These formations grew in complete darkness, one molecule at a time, preserving in their layers a detailed record of past climate conditions through variations in isotope ratios and trace elements incorporated during growth. Cave ecosystems demonstrate life's ability to adapt to extreme conditions. Many caves maintain constant temperatures year-round, close to the average annual surface temperature of their region. Total darkness prevails beyond the entrance zone, and food is scarce, limited to what washes or falls in from the surface or to nutrients carried by groundwater. Despite these challenges, specialized cave organisms thrive. Troglobites, animals that complete their entire life cycle in caves, have evolved striking adaptations, often losing eyes and pigmentation and developing enhanced senses of touch, smell, and chemical detection. Some troglobites have been isolated in caves for millions of years. The salamander species Proteus sanguinus, found in caves of the Dinaric Alps, has lived underground for approximately 20 million years, evolving into a blind, colorless, highly specialized cave dweller. Its metabolism is extremely slow. One study found that individuals can survive without food for up to 10 years, and they may live for up to 100 years, extraordinary longevity for a salamander. In the stable cave environment, life proceeds slowly, without urgency, conserving energy in an ecosystem where resources trickle in sporadically. Underground rivers flow through cave systems, following the path of least resistance through the rock. Some cave rivers are accessible and can be explored by cave divers. Others flow through passages too small or too dangerous for human entry. These rivers may flow for tens of kilometers underground before emerging at springs. The water flowing in these passages today may have entered the cave system decades or centuries ago, moving slowly through the labyrinth of passages, gradually dissolving more rock, carving the passages imperceptibly larger year by year. Aquifers constitute vast underground reservoirs of water held in porous rock or unconsolidated sediment. The water occupies pore spaces between particles or fractures in the rock, moving slowly in response to hydraulic gradients. Flow velocities in aquifers range from millimeters per day in fine-grained sediments to meters per day in coarse gravels or fractured rock. Compared to surface water, which might flow at meters per second in rivers, groundwater movement is extraordinarily slow. Some aquifers contain water that infiltrated thousands or even millions of years ago. The Nubian sandstone aquifer system beneath the Sahara Desert contains fossil water that infiltrated during wetter periods tens of thousands of years ago, when North Africa had a more humid climate. The Great Artesian Basin in Australia, one of the world's largest aquifer systems, contains groundwater that is up to 2 million years old in its deepest parts. This ancient water has been flowing underground since long before modern humans evolved, moving perhaps a few meters per year through the porous sandstone, protected from evaporation, preserved in darkness. Geothermal gradient describes how temperature increases with depth underground, typically about 25 to 30 degrees Celsius per kilometer of depth, though this varies depending on local geology and tectonic setting. This heat flows continuously from Earth's interior toward the surface, produced partly by the decay of radioactive elements in the crust and mantle and partly by the residual heat from Earth's formation. The rate of heat flow is slow, averaging about 65 milliwatts per square meter at the surface, but operating continuously across Earth's entire surface, it represents an enormous total energy output. In regions of active tectonism or volcanism, geothermal gradients are steeper, with temperatures increasing more rapidly with depth. Hot springs and geysers occur where groundwater circulating at depth is heated by proximity to magma or hot rock and then returns to the surface, driven by buoyancy. The water in these systems may have circulated for hundreds or thousands of years before emerging, heated slowly during its time underground, dissolved minerals from the surrounding rock, and now returns fundamentally altered by its underground journey. Underground ecosystems aren't limited to caves. Microorganisms inhabit pore spaces in aquifers and even in solid rock, metabolizing at extraordinarily slow rates in environments with limited nutrients and energy. Some deep subsurface microbes may divide only once per century or even once per millennium, their metabolism slowed to near stasis by the lack of resources. Yet they persist, demonstrating that life can exist under conditions far removed from the sunlight-driven ecosystems of the surface. The subterranean realm operates according to principles different from those governing the surface world. Time scales are longer, changes happen more slowly, darkness is absolute and permanent, temperatures are stable, and seasonal variations don't penetrate beyond the first few meters. It's a world of patience, where water's slow work reshapes rock over millions of years, where organisms live lifespans measured in decades or centuries, where rivers flow for countless generations in channels carved over eons. The underground world persists in its own time, undisturbed by surface weather, continuing processes that began millions of years ago and will continue for millions more. Earth's relationship with the Sun and Moon. Earth's relationship with the Sun and Moon governs the most fundamental rhythms of our planet, the day-night cycle, the seasons, the tides, and the long-term climate variations that have shaped life's evolution. These relationships follow mathematical precision, the result of gravitational interactions and orbital mechanics that have operated with perfect consistency for billions of years. Earth orbits the Sun at an average distance of about 150 million kilometers, completing one orbit in approximately 365.25 days. This distance, called an astronomical unit, places Earth in the Sun's habitable zone. The region where temperatures allow liquid water to exist on a planet's surface. Closer to the Sun, temperatures would be too high, water would exist primarily as vapor. Farther away, temperatures would be too low, water would freeze solid. Earth occupies a privileged position, though the habitable zone is actually fairly wide, and Earth would likely remain habitable even if its orbit were somewhat closer or farther from the Sun. Earth's orbit isn't perfectly circular but slightly elliptical, with the Sun at one focus of the ellipse. Earth's distance from the Sun varies from about 147 million kilometers at perihelion, closest approach, in early January to about 152 million kilometers at aphelion, farthest distance, in early July. This 6.7% variation in distance causes a minor variation in the amount of solar energy Earth receives. About 6% more at perihelion than at aphelion. However, this variation doesn't cause the seasons. In fact, Earth is closest to the Sun during Northern Hemisphere winter, demonstrating that distance isn't the primary factor controlling seasonal temperatures. Seasons result from Earth's axial tilt of 23.4 degrees relative to the plane of its orbit. This tilt means that during part of Earth's orbit, the Northern Hemisphere tilts toward the Sun, receiving more direct sunlight and experiencing summer, while the Southern Hemisphere tilts away, receiving less direct sunlight and experiencing winter. 6 months later, the situation reverses. The tilt's effect on sunlight angle and day length creates the temperature differences we experience as seasons. During summer in a hemisphere, the Sun's rays strike more directly, meaning solar energy is concentrated over a smaller area, heating the surface more effectively. Additionally, days are longer than nights, providing more hours of heating and fewer hours of cooling. These factors combine to produce summer's warmth. During winter, the Sun's rays strike at a shallow angle, spreading the same amount of energy over a larger area, heating the surface less effectively. Shorter days provide fewer hours of heating, and longer nights allow more cooling. The result is winter's cold. At the equator, the sun's angle changes little throughout the year, and day and night are always approximately equal in length. Equatorial regions therefore don't experience seasons in the same way higher latitudes do. Instead, seasonal variations near the equator are often related to precipitation patterns rather than temperature. Many tropical regions experience wet and dry seasons rather than summer and winter, with the timing controlled by the migration of atmospheric circulation patterns like the intertropical convergence zone. Earth's rotation creates the day-night cycle, completing one rotation relative to the Sun every 24 hours on average. This rotation is slowing very gradually due to tidal friction with the Moon, lengthening the day by about 1.7 milliseconds per century. At this rate, it would take about 140 million years for the day to lengthen by 1 hour. By the time Earth's rotation has slowed significantly, the Sun will have evolved into a red giant and engulfed the planet, so Earth will never experience the extremely long days that would result from continued tidal slowing. The Moon orbits Earth at an average distance of about 384,000 kilometers, completing one orbit approximately every 27.3 days relative to the distant stars. However, because Earth is simultaneously orbiting the Sun, the Moon requires about 29.5 days to complete its cycle of phases from new moon to new moon, the synodic month. This is the origin of our calendar month, though most modern months no longer match the lunar cycle precisely. The Moon always shows the same face toward Earth because it's tidally locked, its rotation period equals its orbital period. This synchronous rotation developed over millions of years as Earth's gravitational pull created tidal bulges in the Moon's body. These bulges experienced friction as the Moon rotated, gradually slowing its rotation until it matched the orbital period, at which point the bulges could remain aligned with Earth and the slowing ceased. This is the fate Earth itself is slowly approaching. In perhaps 50 billion years, if the Sun doesn't engulf both bodies first, Earth's rotation will have slowed until it's tidally locked to the Moon, with one face permanently facing the Moon. The Moon's gravitational influence extends beyond creating ocean tides. It also stabilizes Earth's axial tilt, preventing chaotic variations that would occur if Earth had no large satellite. Computer simulations show that without the Moon, Earth's obliquity would vary widely over tens of millions of years, potentially swinging from nearly 0 degrees, meaning no seasons, to more than 80 degrees, meaning extreme seasons with the poles receiving more annual sunlight than the equator. Such variations would cause dramatic climate instability that might have prevented the evolution of complex life. The Moon's presence has been crucial for maintaining Earth's habitability. Solar energy drives essentially all processes at Earth's surface. The Sun radiates approximately 3.8 times 10 to the 26th watts of power, of which Earth intercepts about 174 petawatts, approximately 1/2 of the Sun's total output. This may sound small, but it's approximately 10,000 times more energy than all of human civilization currently uses. Solar energy evaporates water, drives atmospheric and ocean circulation, powers photosynthesis, and maintains Earth's temperature at levels compatible with liquid water and life. The amount of solar energy reaching Earth's surface varies with latitude, time of day, season, and atmospheric conditions. At solar noon on a clear day at the equator, direct sunlight delivers approximately 1,000 watts per square meter. This energy heats the ground, which heats the air above it, creating convection currents that drive weather. Solar energy also warms the oceans, particularly in the tropics, and this heat is redistributed globally by ocean currents and atmospheric circulation, moderating temperature extremes and making much of Earth's surface habitable. Earth's energy budget must balance over long timescales, the amount of energy received from the sun must equal the amount Earth radiates back to space, or the planet will heat or cool. Currently, Earth radiates approximately 240 watts per square meter as infrared thermal radiation, matching the incoming solar energy averaged over the entire planet and over time. This balance has been relatively stable for millions of years, maintained by feedback mechanisms that adjust Earth's temperature until input and output equilibrate. One crucial feedback involves ice and snow cover. Ice and snow have high albedo, meaning they reflect much of the incoming sunlight back to space without absorbing it. When Earth cools and ice cover expands, more sunlight is reflected, causing additional cooling in a positive feedback loop that can lead to ice ages. Conversely, when ice melts, less sunlight is reflected, more is absorbed, and temperatures rise in a feedback loop that can end ice ages. Long-term variations in Earth's orbit and axial tilt, called Milankovitch cycles, influence the distribution and intensity of sunlight reaching Earth, driving ice age cycles over tens of thousands of years. Three main cycles contribute: eccentricity. The shape of Earth's orbit varies from nearly circular to slightly elliptical over approximately 100,000 years. Obliquity. Earth's axial tilt varies between 22.1 and 24.5 degrees over approximately 41,000 years, and precession. Earth's axis wobbles like a spinning top, completing one cycle every 26,000 years. These cycles don't significantly change the total solar energy Earth receives, but they alter how that energy is distributed seasonally and geographically, particularly affecting the amount of summer sunlight at high northern latitudes. When these cycles align to reduce summer sunlight in the far north, snow that falls during winter doesn't completely melt during summer, accumulating year after year and gradually building into massive ice sheets. The most recent ice age, which began about 2.6 million years ago during the Pleistocene epoch, consisted of many glacial and interglacial periods. During glacial periods, ice sheets kilometers thick covered much of North America, Northern Europe, and Asia, while global sea levels dropped by more than 100 meters as water was locked up in glacial ice. During interglacial periods, the ice retreated, sea levels rose, and climate warmed to conditions similar to or even slightly warmer than today. We currently live in an interglacial period called the Holocene epoch, which began about 11,700 years ago when the last major ice sheets retreated. Based on past patterns, without human influence, Earth would likely eventually drift back toward glacial conditions over the next several tens of thousands of years as Milankovitch cycles shift toward configurations favoring ice sheet growth. The Sun itself has been slowly brightening throughout its lifetime. When the Sun first formed about 4.6 billion years ago, it was approximately 30% dimmer than it is today. This presents a puzzle called the faint young sun paradox. With 30% less solar energy, Earth should have been frozen solid during its early history, yet geological evidence indicates liquid water existed on Earth's surface at least 3.8 billion years ago, and possibly even earlier. The resolution likely involves greenhouse gases. Early Earth's atmosphere probably contained much higher concentrations of carbon dioxide and possibly methane, providing a strong greenhouse effect that kept the planet warm despite the dimmer sun. As the Sun has gradually brightened over billions of years, Earth's atmospheric carbon dioxide levels have decreased, partly due to the weathering of silicate rocks, which consumes carbon dioxide and locks it away in carbonate minerals. This negative feedback has helped maintain relatively stable temperatures despite the increasing solar luminosity. The balance isn't perfect. Earth has experienced periods much warmer and much colder than today, but it's been sufficient to keep most of the planet's surface within the temperature range where liquid water can exist for billions of years, allowing life to persist and evolve. The Sun will continue brightening, increasing in luminosity by about 10% per billion years. In approximately 1 billion years, the increased solar output will warm Earth enough that weathering processes will accelerate, drawing down atmospheric carbon dioxide to levels insufficient for photosynthesis. Without photosynthesis, complex life will become impossible, though simple life might persist in favorable microenvironments. The oceans will gradually evaporate, and Earth will transition toward a Venus-like state with a thick atmosphere and surface temperatures hot enough to melt lead. Eventually, in about 5 to 7 billion years, the Sun will exhaust the hydrogen in its core, expand into a red giant, and likely engulf Earth entirely, vaporizing whatever remains of our planet. But these are concerns for the incredibly distant future. For now, and for millions of years to come, Earth will continue orbiting the Sun in its stable, nearly circular orbit, receiving steady solar energy, maintaining liquid oceans, and supporting life. The Sun rises each morning with the dependability of clockwork, following the same patterns it has followed for billions of years, warming the planet, driving weather, enabling photosynthesis, making life possible. The relationship between Earth, Sun, and Moon creates rhythms that govern biological and physical processes. Circadian rhythms, internal biological clocks that match the approximately 24-hour day, are present in virtually all organisms from bacteria to humans. These rhythms optimize biological functions to match the day-night cycle, anticipating dawn and dusk rather than merely reacting to them. Many animals also respond to lunar cycles, particularly marine organisms whose reproductive timing often coordinates with spring tides during full and new moons, ensuring that eggs and larvae are dispersed effectively by strong tidal currents. The regularity of celestial mechanics provides a foundation of predictability in an otherwise chaotic natural world. We can calculate the exact time of sunrise 10,000 years in the past or future with remarkable precision. We know when eclipses occurred in ancient times and when they will occur centuries from now. The seasons will continue their eternal cycle, summer following spring, autumn following summer, winter following autumn, spring following winter, year after year after year, driven by Earth's unchanging tilt and its steady orbit around the Sun. The Moon will continue its phases, waxing and waning, pulling tides in and out, just as it has for billions of years. There's a profound comfort in this predictability. While human affairs are uncertain and unpredictable, the celestial dance proceeds with absolute precision. The Sun will rise tomorrow morning at the calculable moment. The Moon will reach its next full phase exactly when mathematics predicts. The summer solstice will occur when Earth reaches the precise point in its orbit where the northern hemisphere tilts maximally toward the Sun. These events require no maintenance, no intervention, no attention. They simply happen, following laws of physics that have never varied and never will, for as long as the solar system exists. Closing reflections. As you drift deeper into rest, let these thoughts settle gently around you like falling snow. Earth has been here for 4.5 billion years, and it will be here long after you wake tomorrow morning. The continents will continue their patient drift across the globe, moving at the speed your fingernails grow, reshaping themselves with such leisurely confidence that entire supercontinents form and break apart without hurry. Mountains will rise grain by grain and erode away particle by particle, following the same patient rhythms they've followed since Earth's crust first solidified. Water will continue its eternal cycle, evaporating from the oceans, drifting as invisible vapor on the wind, condensing into clouds, falling as rain, soaking into soil, percolating through rock, emerging from springs, flowing in rivers back to the sea, beginning the journey again. The water molecules in your body right now have been part of this cycle for billions of years, and they'll continue long after they've moved on to other purposes. You are made of borrowed stardust and ancient water, assembled temporarily into your particular form before dispersing again into Earth's great cycles. The atmosphere surrounds you, held by gravity, protecting you from radiation, moderating temperatures, providing oxygen with every breath. This invisible ocean of gas has been performing these services for billions of years, and it will continue for billions more, following physical laws with perfect consistency. The magnetic field extends outward from Earth's core, deflecting solar wind, creating auroras, guiding migrating birds, operating without pause or variation according to the same electromagnetic principles that have governed it since the dynamo began. Underground, water flows through ancient aquifers, moving perhaps a few meters per year through the darkness, patient and persistent. Caves grow larger, one molecule at a time, stalactites reaching down and stalagmites reaching up, growing so slowly that a human lifetime sees no change, yet given enough time they'll meet and form columns. Deep in Earth's mantle, rock flows like thick honey, driving the tectonic plates that have been reshaping the surface for billions of years. Life evolves, one generation at a time, one small change at a time, accumulating modifications over millions of years until simple organisms become complex, single cells become multicellular, aquatic organisms become terrestrial. The process has operated for nearly 4 billion years and will continue for hundreds of millions more, until the sun eventually grows so bright that Earth's oceans boil away. But that's a billion years in the future. Enough time for evolution to play out countless more transformations, enough time for geological processes to reshape the continents dozens more times. The sun rises and sets with perfect regularity, following Earth's rotation, which has been spinning for billions of years and will continue spinning for billions more, gradually slowing due to tidal friction but so gradually that the change is imperceptible across human timescales. The moon orbits Earth, creating tides, stabilizing Earth's tilt, reflecting sunlight in its predictable phases, a celestial companion that has been circling our planet for over 4 billion years. All these processes continue whether you're aware of them or not. They operated the same way last night while you slept. They'll operate the same way tomorrow night. They operated before you were born and will continue after you're gone. This isn't meant to be melancholy but comforting. You're part of something much larger and longer lasting than your individual concerns. Your worries are real and valid within the human sphere, but against the backdrop of geological time, they're momentary ripples on an ocean of stability. So let yourself relax completely. Let the tension drain from your muscles. Let your thoughts slow and soften. Earth has everything under control. It's been doing this for 4.5 billion years, and it knows what it's doing. The planet will keep spinning, the sun will keep shining, the moon will keep orbiting, the continents will keep drifting, the water will keep cycling, life will keep evolving. These processes are so much larger than you, so much older than you, so much more patient than you could ever be. You don't need to maintain Earth's systems, they maintain themselves. You don't need to keep the sun burning, fusion in its core will continue for billions of years. You don't need to keep the moon in orbit. Gravity handles that automatically. You can let go of everything, surrender to rest, and trust that when you wake, the world will still be here, following the same reliable patterns it's followed for eons. The ground beneath you is solid, held together by electromagnetic forces between atoms that have been stable since those atoms formed in ancient stars. The air around you moves in response to pressure differences, circulating endlessly, mixing and spreading and never running out. The water in your body came from Earth's oceans and will return there eventually, part of the endless cycling that has continued for billions of years. You are safe on this ancient planet, wrapped in its protective atmosphere, warmed by its star, stabilized by its moon, part of systems that dwarf your individual existence but embrace you nonetheless. Nothing requires your attention right now. Nothing demands your concern. Earth will keep being Earth, following laws of physics and chemistry that never change, never tire, never need rest. So rest. Let sleep come naturally. Let your breathing slow to match the patient rhythms of the planet, slow like continental drift, slow like erosion, slow like the growth of crystals in a dark cave, slow like the evolution of species over millions of years. You have all the time in the world because the world has all the time there is. 4.5 billion years behind it, billions more ahead, and you get to be part of it, right now, in this moment, breathing and resting and being exactly where you are. The facts we've explored tonight are just a tiny sampling of Earth's countless wonders, but they all point to the same truth: our planet is ancient, stable, patient, and persistent. It has weathered every catastrophe, survived every ice age, adapted to every change, and continued for billions of years. It will be here tomorrow, and the day after, and for millions and billions of days beyond that, spinning in space, following its orbit, maintaining life, being Earth. You can trust in that stability. You can rest in that knowledge. You are held by gravity, surrounded by atmosphere, warmed by the sun, part of the same matter that has existed since the universe began, arranged temporarily into your particular form, experiencing consciousness for this brief window before returning to the great cycling of atoms that makes up all of existence. And with that comforting knowledge, let yourself drift completely into sleep, into dreams, into the unconscious rest your body needs. Earth will keep doing what it's always done, and when you wake, refreshed and restored, it will still be here, solid and dependable, continuing its ancient journey through space, carrying you with it, as it always has and always will. Thank you so much for spending this time with us tonight exploring the peaceful facts about our remarkable planet. If you found this helpful for falling asleep, I'd truly appreciate it if you'd hit that like button and consider subscribing to the Deep Science Sleep channel. Your support helps us create more content like this, more soothing science stories to help you drift off into restful sleep. Sleep well, rest deeply, and we'll see you in the next video. Good night.